Hope you're trying to have a productive day. In this video, we will be deriving the equation t is equal to 2 pi times the square root of L over G, where t is the period of oscillation, L is the length of the pendulum cord, and G is gravitational acceleration. Now, how do we get at this equation here? Well, let's draw some diagrams. So I'm going to draw the first diagram, and this is going to be the diagram of the simple pendulum when it is at equilibrium position, meaning there is no angle of displacement. And this is the bob at the end of the pendulum, or this is the mass at the end of the pendulum, right? There's a force that acts vertically downwards, and that force is mg. There is also a force in the string, and that force is tension, but the tension here is not the same as period here, even though they're both t. So for now, let us just ignore tension. We do not need it for this derivation for the most part. What we do need, though, is to recognize that the length of this cord, which means the distance from up top to down at the bottom, that distance is L, and that's where this L comes from, right? Now let us redraw the pendulum after it has gotten an angle of displacement. What do I mean by that? Well, let me just redraw the pendulum. Right then, so we have the equilibrium position here, but now we have displaced the pendulum in that direction, right? We've pulled it that way, and now it's going to be here. The angle between the equilibrium position and the new position is what we call theta for this scenario. Now let us also draw some more forces acting on the bob. So we're going to have a force like this, and that force is the same as the force down here that acts downwards. That force would indeed be mg, or the weight. There is also going to be another force acting like that. We're not really concerned with that force particularly. The force we're concerned with is the force acting like that. That force is minus ma, negative ma, right? And that's the force that we are concerned with. Now, the angle here, you can see, would be the exact same angle here. So we're going to get theta again. And this angle here is 90 degrees. So what we have is a right angled triangle where mg is the hypotenuse. This force here is the adjacent side, and negative ma is the opposite side. Now we're going to try to find negative ma, but we're going to find negative ma in terms of mg. So negative ma is equal to what exactly? What exactly is negative ma equal to? Well, we can do some trigonometry. We have the hypotenuse, which is mg, and we have the opposite side, which is negative ma. And when we have the opposite over the hypotenuse, what we get is sine theta. So basically, if we wanted to find the opposite, which is negative ma, all we would have to do would be multiply this side by the hypotenuse, and then multiply this side by the hypotenuse. So the hypotenuse cancels over here, and we're left with the opposite side is equal to sine theta times the hypotenuse. So let's write that over here. The opposite side, negative ma, is equal to sine theta. So we can write sine theta multiplied by the hypotenuse. The hypotenuse here is mg, so we rewrite mg. Now sine theta for a small angle is going to basically be the same thing as tan theta, and this angle, even though it does look small, it is supposed to be small. The only reason the angle is large is because I didn't want the diagram to be too small and everything to be squeezed into one area, so I made the angle large. But this angle here, right here, theta, that angle is basically small. When an angle is small, sine theta is the same thing as tan theta, or it's basically the same thing as tan theta. So what is tan theta in this instance? Well, let's call this distance, the distance that we displaced it by, let's call that distance x. And remember that over here, the length of the string was L. So this side over here is L. So we have L and we have x, and we want to find tan theta. Tan theta is going to be the opposite, which is x, over the adjacent, which is L. L is the adjacent, right? So instead of writing sine theta, we can write negative MA is equal to tan theta times mg, or we can just basically say negative MA is equal to mg tan theta. And I'm writing like this because I don't want to put the multiplication sign right now, because there's going to be a term called x later, and I don't want the multiplication sign to be confused with x. So let us drop the multiplication sign and let's just write mg tan theta, right? So now that we have this, we can rewrite the tan theta, and this is where the x comes in. So negative MA is equal to mg times tan theta. Tan theta is going to be the opposite, which is x. So this is where the x comes in, over the adjacent side, which is L. So we have mg times x over L. Now we can divide both sides by m, and we're going to be left with negative a is equal to g times x over L. We can rewrite this and say that negative a is equal to g over L times x. Now, an equation for simple harmonic motion has the formula for the restorative acceleration. The restorative acceleration in simple harmonic motion, negative a, is equal to omega squared times x. Now, x is the same here, and it's the same there. A is the same there, and it's the same down here. Which means that if these two are the same and they're the same equation, that must mean g over L is actually the same as omega squared. So let us rewrite that one bit of information. That was omega squared is equal to g over L. We want to find period. Where does period fit into this? Well, it turns out that omega, which is this here, omega is equal to 2 pi over the period. And now that we have it squared, we're going to just square everything. And that would be equal to g over L. Now let us invert both sides of the equation, and we're going to get t over 2 pi all squared is equal to L over g. Now let us find the square root of both sides. So we find the square root of this side, it cancels with the square there, and now we're going to find the square root of L over g. So now we're left with t over 2 pi is equal to the square root of L over g. Now all we have to do to find t is multiply this side by 2 pi and then multiply that side by 2 pi. And now you can see that this translates up here to t is equal to 2 pi times the square root of L over g. And you can see now that this equation here is the same as the equation that we started out with over here. So we have just proven using some diagrams and some trigonometry that t is indeed equal to 2 pi times the square root of L over G. What is period, by the way? Period is basically the time it takes to complete one oscillation. So if you do one oscillation in 1 second, then the period is 1 second. With that, we have come to the end of this video. So as always, thank you all for watching, and I hope you've learned something.